I received. I drank the other one, I have to confess. So thank you very much. And if it's late enough in the day for you to have champagne, then I encourage you to have it. This talk will be more enjoyable if you've had some. All right.
Thanks.
So I thought that I would provide an update on the Hubble tension and particularly focus on recent contributions in the last year from the James Webb Space Telescope to this interesting problem. So let me just give a little bit of background. I think many of you are familiar with this problem, but of course, we look at the expansion of the universe around us to learn about its composition, its age, and its fate. Generally, we assume the universe is homogeneous and isotropic on large scales, and that it obeys general relativity. And from that, we can derive the Friedmann equation, which is a differential equation that describes how the scale factor A, the size of the grid that you see, how that changes as a function of time in response to the physics of the universe, which is on the right-hand side of the Friedmann equation. So that's the mass density, vacuum energy, any other components that gravitate, and perhaps complex geometry. Now, we cannot directly observe A and T, but we observe proxies. A, we observe redshift, and instead of time, we try to measure distances. And through knowledge of the speed of light, we can infer the relationship between A and T. And so in the observer's frame, this is, of course, is the Hubble diagram. And if we can observe very far away objects, then we are probing the past and learning the expansion history of the universe. So this goal of measuring A of T to learn about the universe was once thought to be simpler than it is now. When we thought we lived in a matter-dominated universe, then just the first two derivatives of A were what we needed to know. The first, of course, is the Hubble constant that sets the size scale and age scale for the universe. And to measure the Hubble constant, you need to measure absolute distances as a function of redshift. The second derivative, Q naught, the deceleration of the universe. For this, we need to measure changes in distance with redshift, or changes in the expansion rate of the universe. And the 1990s was really a special time, and since then, for measuring these quantities, because of the development and better technology that allowed us to measure truly long-range distance indicators. So speaking of distances, I'm going to be talking about measuring distances with standard candles. These are objects whose luminosity is well understood so that we can measure their distance by measuring their brightness. So I'm going to be talking about type 1a supernovae, which are exploding white dwarf stars. These reach billions of solar luminosities when the white dwarf star approaches the Chandrasekhar limit, either probably because it's in a binary, but either because of overflow from companion or perhaps even merger of two degenerate stars. And I will be talking about Cepheid variables. These are supergiant stars that pulsate with a frequency or period that tightly couples to their mass scale and luminosity scale as understood from pulsation theory. These are very luminous, hundreds of thousands of solar luminosities. Cepheids are more common in galaxies, of course, than type 1a supernovae, and we will use both of them. In practice, we sometimes have to standardize these objects. They are not perfect standard candles, but they are often standardizable. We also measure colors to account for dust and the reddening effects of dust. And just to emphasize, as I mentioned a moment ago, in order to measure Q naught, we really only need to be able to measure relative distances. We don't need absolute distances. So type 1a supernovae were sufficient back in the 1990s, even uncalibrated, because we could just measure their brightnesses to tell us relative distances. So most of you are aware, I'm sure, that by the early 2000s, there had been a lot of progress in this field. It had been determined by my colleagues and I using high redshift supernovae that Q naught was negative, that is, the universe is accelerating. And the first generation of measurements of the Hubble constant from the HST Key project and others came in with H naught of about 72. I sort of jokingly think to myself, if someday in the future we have time travel and I could go back to an earlier point in my career and change paths, this might be the point at which I should, because it's always possible once things are in kind of consensus to break that. And that's what I'm going to be talking about going forward. So, of course, we didn't stop here. Our field didn't stop here. We wanted to understand, why is the universe accelerating? We don't really know. We generally talk about dark energy, but to be a little more specific, we talk about vacuum energy. That would be a cosmological constant as being a fixed quantity, fixed energy density over time. Another possibility closely related would be a field, a scalar field whose potential energy looks like vacuum energy for a while, but it might change over time. Very different causes for a similar phenomenon. And the third possibility would be a modification to general relativity as we get to large scales. As the scale factor approaches 1, perhaps general relativity fails. Now, the quantitative test of these three possibilities is to measure the equation of state of dark energy, because we would expect to see -1 for option 1, perhaps something other than -1 for option 2, or a derivative that's not 0, or for option 3 to see a scale dependence of measurements of W. And so this is the motivation for future missions, which will target this, the Roman Observatory, the Euclid Observatory, Rubin, and we look forward to those results. But in the meantime, what is most common these days in cosmology is to assume option 1, particularly because option 1 is the easiest to calculate. That is, you can make predictions based on option 1, whereas option 2 and 3 are kind of amorphous, a sort of a cloud of possibilities. So to make progress, therefore, and to understand this model better, it is often most useful to assume the simplest form of lambda CDM and then look for departures from that. And I'm going to talk the rest of this talk about the search for departures by looking at the Hubble constant. So that was the first number I talked about in the beginning of this talk. So generically, a lambda CDM model will have two phases of expansion. It will have a dark matter dominated phase at early times where the expansion will be decelerating. And then it will have the dark energy dominated period where it will be accelerating. And with very precise measurements of the cosmic microwave background, for example, from Planck, we can calibrate the model by comparing the fluctuation spectrum that we would expect in the early time plasma of the universe based on the model to the temperature anisotropies that we see in angular coordinates on the sky. And it's to reach agreement between the model and the observations, we vary 6 parameters of the model. These change the predicted power spectrum until you get a good match. And then we consider the model calibrated, and then we can use the model, once calibrated, to predict the entire expansion history of the universe to the present time, to predict the value of the Hubble constant, 67.4 plus or minus 0.5, a very precise prediction. However, there's a lot of phenomenology in this model. We don't really understand dark energy and dark matter at a deep level. We've made very vanilla assumptions about them, taking their simplest form. And so it's very powerful to test this model by directly measuring the Hubble constant at the present time through the combination of distance and redshift measurements. So just to say a little bit more about the distance measurements I'm going to be talking about. This is the construction of a 3-rung distance ladder that is used to measure long-range distances. We start with geometry. It could be parallax, it could be detached eclipsing binaries, or the masers in NGC 4258 in Keplerian motion. Those are used to calibrate Cepheid variables, which I mentioned earlier, in the galaxies nearby, within about 40 megaparsecs, that recently hosted a Type 1a supernova, and then the Type 1a supernovae all the way out to the Hubble flow to measure the expansion of the universe. So as I mentioned earlier in my talk, this was done very well by two teams in the late 1990s to measure the Hubble constant to about 10% precision. We started a project called the SHOES project a few years after that to try to reach percent level precision to be a good complement to the cosmic microwave background. And this generation 2 experiment was based on about 20 successful HST proposals over the last 20 cycles, about 1,000 orbits in all, and now 2 cycles of JWST observations. The key elements of SHOES to improve upon past measurements were to make use of the same telescope, HST, for the Cepheid measurements between rungs 1 and 2, so that we could cancel flux calibration errors that were an issue in the past. We make our observations in the near infrared, unlike the largely visual observations of the earlier generation, to reduce the effects of dust. We use higher quality supernova data than was available some 20 or 30 years ago from the Pantheon Plus survey. Thorough error analysis, propagation of errors, keeping track of covariance, variance to the analysis, and public release of the data so that other people can replicate this work, and that's been done many, many times. After 15 years of data collection, we have now observed Cepheids in the hosts of 42 Type 1a supernovae and calibrated them with 3 independent geometric calibration sources. So I consider this a pretty ideal data set for this measurement. I can't complain that we have not received the time we needed to make these measurements. In fact, we really have received quite a great amount of time to do this. And so what I'm showing here is the 3-rung distance ladder from our data release 5 as of last year. Rung 1, as I said, geometry calibrates Cepheids. Rung 2, Cepheids calibrate the Type 1a supernovae, and rung 3, where the Type 1a supernovae measure the expansion of the universe. Okay, so I'll cut to the chase. You likely have heard about this problem before, and the problem, the origin of it, is the fact that when we make the measurements with the previous described experiment, we get a Hubble constant of 73 plus or minus 1. This is a full 5 sigma from Planck's predicted value based on lambda CDM. If we use some recent updates, either Cepheids in clusters from Gaia or spectral matching, we're up to somewhere around 5.7 sigma. So at this point, this is a very serious tension. We went through many variants of the analysis, 12 categories of 67 variants, bifurcations and extensions. These are some of the ones that people have focused the most on. And the bottom line for us is it's very difficult for us to get below about 72.5 or above about 73.5. So this is the status as of last year. Now, of course, this is not just something that we see in our measurements. I would say this is broadly seen by the community. If you use any one of a number of ways to start at the early universe with different cosmic microwave background data sets, or you calibrate baryon acoustic oscillations using the cosmic microwave background, you tend to get an answer around 67 or 68. On the other hand, if you make measurements of distances and redshifts through a combination of different ladders or even no ladder at all, like directly with masers, you tend to get this higher value. The full range is about 70 to 75, but they're well described by a sort of characteristic value of around 73. I would direct you to this recent annual review that just came out, I think, a week ago from Lecce-Verde and collaborators, reviewing the status of the Hubble tension. And this is a summary plot like the one I just showed you before, with a slightly different selection of different measurements. The bottom line here is that if you look at all the precise measurements, none of them are coming in on the other side, lower than the Planck value. This is quite noticeable and is a restatement of the problem that this is an incredibly unlikely draw from the value from Planck. And so we're pretty convinced that something is going on. Now, this is not a new realization. This has been around the awareness of this for about 10 years. This would be my top 10 list of different ideas of where the problem or error could be if it's not new physics, because if it is not an error, then it is new physics, and that would be incredibly exciting. So it's important to go through a list kind of methodically. I don't have time to cover the first 9 of these, except to say that they're really ruled out. And if you hit this QR code link, it will take you to a spreadsheet that goes over these 9 in more detail, showing you which papers are drawing conclusions on these. I'm going to focus on number 10, near-infrared Cepheid crowding, because this is something that we can newly address with the James Webb Space Telescope. So let me explain this idea. The idea here is that when we look at Cepheid variables in the hosts of type 1a supernovae, because of limited resolution, we see those Cepheid variables superimposed on a scene with other stars. And this effect is known as crowding, and we have to account or correct for crowding by throwing fake stars into the images of known brightness to assess the background and correct for this. This is done with artificial stars. I would not say that this is a source of bias because we are accounting for it, but it is the largest source of noise in the measurements because it's a statistical accounting for something that varies individually. What's much better is to have a telescope with much higher resolution in the near infrared, and that's what we now have with the James Webb Space Telescope. And so as a result, the Cepheids are no longer crowded. They generally sit on, I would say, flat or naked backgrounds, so we can measure the Cepheids without this noise. Just to look in a little more detail at the different sources of noise, this is the scatter in the period luminosity relationship of Cepheids. Here are some period luminosity relationships, for example, in the Large Magellanic Cloud. And the noise depends on what wavelength you're at, what contributes. And so generally, we stay away from short wavelengths because of the impacts of dust there. But if we go too far to the red, we lose resolution, we lose contrast with the background. We want to be where the Cepheids are brighter. And so the sweet spot seems to be about the near infrared, maybe somewhere around 1.5 microns or so. But that's where Hubble had relatively poor resolution. And so JWST is now giving us the best of both worlds. It gives us the resolution that Hubble only ever had in the optical, but it gives us the low dust that we need in the near infrared, and JWST gives us that in a single image. So in our cycle, our first 2 programs, we are observing, reobserving the Cepheids in galaxies that host 15 type 1a supernovae in 3 filters, a F090W, which is sort of like the I band, F150W, which is really the key. That's very similar to HST's band, where all the past near-infrared measurements were made, and a longer wavelength, 2.8 microns. We observed the Cepheids in 2 epochs, not just one. Why 2 epochs? Well, we want to confirm our astrometric identification of the Cepheids, and so we want to see that things vary. We want to test the stability of JWST. It's a complex telescope, and when it was first launched, it was not clear how stable the telescope would be. And we need to, or we would like to be able to rephase the Cepheids because we know their periods, but knowledge of their phase has been lost since they were discovered by Hubble, in many cases 10 or 15 years ago. So we just completed our cycle 1 observations. We've published the first 2 hosts. That's NGC 4258, which is the calibrator, and NGC 5584. I'm going to show you results from 4 more hosts in prep. And then in cycle 2, we'll be observing another, 6 hosts of 8 more type 1a supernovae. And there's also a program by the CCHP in cycle 1 that is observing the nearest hosts. Okay, so these are the first two we observed in February and May. The upper panel shows you the footprint of JWST as we observed it. We observed these in two epochs, so we hit both sides of the galaxy, and in 5584 we hit the disk and this off disk field. Now this shows you the JWST images, more than 100 Cepheids in NGC 4258 and more than 200 in NGC 5584. We were concerned whether the telescope would be stable enough for photometry, and it turns out we needn't have worried. The JWST project is monitoring the wavefront of the telescope every couple of days, and if any of the mirrors go out of alignment, they are corrected. And so I'm showing that here. Over the course of our observations, there was a few small hiccups and corrections that occurred. This line is the corrections, but none of them actually occurred at the time of our observations. So the wavefront modeling shows us variations in photometry down at the core of the PSF would be less than 5 millimags. Okay, here are the color magnitude diagrams of the first two galaxies we observed. The position of the Cepheids is shown here as these stars. They live in this kind of, known as the instability strip, but this kind of yellow color region in between the red giant branch and younger, bluer stars. So that's just where they were expected to be, of course, and they're individually found within about 0.3 pixels or about 0.01 arc seconds of their expected position. Here are postage stamps showing you for NGC 5584 what the Cepheids look like in the different filters. I'm going to zoom in here or focus you on the difference between HST and JWST at the same wavelength. You can see that the difference in resolution is really quite dramatic. This is the great gain we're making, is the ability to cleanly separate the Cepheids from other stars. That gives us higher precision photometry. That is a very important part of these measurements. As I said, we observed the Cepheids in two epochs. So what I'm showing you here is the difference in the brightness of the Cepheids between those two epochs as a function of the log period. Most of the Cepheids live along this ridge that you see here that agrees very well with the simulations, which are seen in gray. The reason for that is because we are observing Cepheids over various phases, but because their light curves are asymmetric, they rise quickly and they fall very slowly, you're most likely to find them declining. And declining here corresponds to this, the sort of greenish or bluish part here of this color-coded curve, which is why we generally find them here. However, we can compare the difference measurement to the simulation to constrain the phase to recover knowledge of the mean magnitude of the Cepheid. So just sort of cutting to the chase, here is the period luminosity relationships for these two galaxies, the anchor NGC 4258 and the supernova host NGC 5584. In gray are the observations from the Hubble Space Telescope, and in red from JWST. So what you see here is a really dramatic improvement in the data quality. The scatter is reduced by a factor of 2.5. But the intercepts, the things that measure the distance, are quite consistent, and we only care about the difference in the intercepts to measure distances, and so those shown here are in very good agreement between JWST and HST. So we can measure the distance to this galaxy and others with this distance ladder now using JWST. And so comparing to past measurements of the distance to this galaxy, you can see it agrees very well with our previous results from 2016, a reanalysis by the Arakaria project by Javan Marty and collaborators that went back to the original pixels and did this measurement themselves. Then our reanalysis in 2022, and then this JWST measurement, the baseline result, as well as other filter combinations, all in quite good agreement. But all quite a bit different than the expected value if you build a distance ladder in the reverse. You start with the cosmic microwave background and you walk that all the way back to this galaxy. You would expect quite a bit of a different distance. This difference here is a manifestation of the Hubble tension even for a single galaxy. So I think from these observations, it's pretty clear that systematic errors in HST Cepheid photometry do not play a significant role in the Hubble tension. This particular galaxy was actually quite a strong test because it had the best combination of distance. It was relatively close to the mean of the supernova sample and one of the largest sets of Cepheids. So it gave the best statistics. If there was a systematic error, we would have expected to see it even in this first set of observations, but that's not the case. I also want to mention this data can be used to measure other distance indicators, so-called standard populations instead of standard candles, but a similar idea. The tip of the red giant branch is a feature of the brightest that red giant stars become before they ignite helium. And that can be measured in the outer module here from the old stars, or a feature called JAGB, which is our AGB stars that are carbon rich, that form this kind of cloud over here that can be measured in the outer disk. And so Gagandeep Anand, who is one of our collaborators on this project, has been busy measuring the tip of the red giant branch distances with the JWST data. The first measurement, actually, I'll show you a couple, are in very good agreement with the Cepheid measurements. We've also been looking at the JAGB feature because it's quite prominent in our data as well. So you could look forward to, I think, additional distance indicators. Just to show you overall, if you measure the distance to the same type 1a supernova hosts with either Cepheids or tip of the red giant branch, and this is from 3 different sets now, from EDD, from CCHP, and from JWST now. They're in very good agreement. I'm showing you the differences here. The most 2 recent measurements in red here are the new ones from JWST, shown right here. So we see very good agreement between Cepheids and tip of the red giant branch when they are calibrated with the same anchor, NGC 4258. Okay, so the previous results I talked about with the Cepheids were published about 2 or 3 months ago in the paper I cited on the title page of my talk. I wanted to show you a little bit more progress. So 4 recent type 1a supernova hosts that we just observed in the summer of 2023, this summer, NGC 1448, NGC 1559, 5468, and 5643. Again, showing you the regions that we observed in 2 epochs, and the little dots that you see here are the positions of the Cepheids. Again, we monitored the wavefront. There was 1 hiccup in the telescope around July 13th in the C5 segment, which got a little bit out of alignment. You see it right over here in this hot spot, and you see the inverse of that as it was corrected. Again, we were very fortunate that that didn't strike any of our observations. And again, wavefront modeling indicates that we would have errors of less than 5 millimags between our observations. Here are the color magnitude diagrams of the 4 new galaxies, showing you, again, the position of the Cepheids, very consistent with the expected colors of these. And now what I'm showing you are postage stamps, just 2 Cepheids for each host, so you can see sort of across all the samples. And again, just zooming in, I think I could do this all day, is just stare at these JWST images in comparison to the HST version. It's hard to describe, but I've spent about the last 10 years studying and measuring the bottom row, and often frustrated that the resolution wasn't better. So this is just like absolute magic to me to get to use a telescope with such great imaging. And I'm extremely grateful to the people who built this telescope, designed it, developed it, advocated for it, risked a lot of their time and energy on this. It's been a 30-year odyssey. And I'm just so thrilled that we're able to see some of this payoff from it in such outstanding image quality. Here's more of those phase recovery diagrams that we use to recover the phases of the Cepheids for these 4 hosts. And then here is the sum total of all the period luminosity relationships we've measured now. This is about 1,000 Cepheids in 5 hosts of 8 type 1a supernovae plus NGC 4258. And we see the same story in all these galaxies, which is a consistent factor of 2.5 reduction in dispersion relative to the HST observations. And now if we compare as a function of distance, the difference between the JWST and HST distance measurements, the baseline here is black. That's the same system that we used to measure them originally with HST. It's just changing the near infrared filter from HST to the JWST version. You see very good agreement, and then we have a couple other filter combinations that we can use, also yields good agreement. Now, if you were to have solved the Hubble tension by finding some bias that became clear with the JWST observations, and if that bias was linear, if it grew starting at the calibration, it grew with distance so that it became large enough to solve the Hubble tension. That is the 5 log, the higher Hubble constant over the lower Hubble constant, 0.17 magnitudes would be the size of the bias at the mean of the sample. We can rule out that linear trend. As you see, it's quite inconsistent with the data at more than 8 sigma. So I would say at this point, our evidence against an error in the Cepheid photometry is stronger than the evidence of the tension itself. And so I don't see any way this could be a significant contributor to the tension. So we continue to expect to make some gains in local measurements of the Hubble constant over the next few years, probably most notably from Gaia data release 4 and 5, although we're also working, Luisa Bruval is working on another anchor in the Small Magellanic Cloud, and there will be other groups that I mentioned before and more who are contributing undoubtedly to some of the excellent measurements that can be done with JWST. I wish I could tell you what the cause of the Hubble tension is. It's a very interesting and hot topic in cosmology right now. There's no consensus, but it seems easiest based on the ideas proposed if you were to make an alteration to lambda CDM to do that before recombination. If you could, for example, inject more energy in the early universe, more inhomogeneity, another particle, another field. Most of those would go in the direction of causing the universe to expand faster before recombination, making the universe become transparent earlier, which reduces the effective sound horizon, which essentially calibrates the cosmic microwave background and baryon acoustic oscillations. There have been lots of ideas proposed for this. I'll just direct you to some of the recent reviews, which sort of score and rank these. Some are more successful than others. I think it's a very interesting area of research. I also think that more cosmic microwave background data, particularly at high frequencies, high L, and polarization, has the potential to see signatures of pre-recombination new physics that some of these models predict. There's been claims or hints maybe that has been seen, or maybe it hasn't, but it certainly demonstrates how such data could, in principle, be helpful for this. One curious feature that I remain intrigued by, I think there are some large-scale CMB anomalies, which many people have pointed out, which if we have the right model, might in the end be just statistical fluctuations. But if the model has some problems and is breaking, then in hindsight, when we figure out why, we might look back on some of these large-scale anomalies as clues. And so I just point you to, again, Lecce-Verde's review that goes over and points out some of these, like the split in the anisotropy spectrum in the middle, which would pull towards either a lower Hubble constant at high L or a higher Hubble constant at low L, as one that I've always found kind of intriguing. Okay, so at this point, I think the data is gotten very good and presents a formidable challenge to us. If it's new physics, then it has to be just so, because we have very good data from the cosmic microwave background and H of Z probes. So you can't just run wild. It has to be consistent with the data. But I think it's very difficult to say it's systematics because it's been 10 years. And I think all of the main ideas of what that could be have been ruled out by independent rungs, duplicate measurements, specific experiments. Short of a massive failure of the Copernican principle, I don't see a way to do this because all the various tests have been passed. Fortunately, for most astronomers, they don't need to know the Hubble constant to the precision that we're looking at. So, if you need to know a value, just pick one. But I think for people to understand, the reason we're so fascinated by the Hubble tension is these are really our best two approaches to measuring or predicting the value of the Hubble constant. The cosmic microwave background is absolutely key to our understanding of the universe, but so are distance indicators that have been used to learn that the universe is expanding in the case of Cepheids, or that the universe is accelerating in the case of type 1a supernovae. So again, these are sort of our gold standard tools. We want to understand why they don't agree. And I think that is a very interesting question. So I'll conclude this discrepancy, at least 5 sigma, has been around for about 10 years. A simple summary, there's really not precise measurements of the late universe that are coming in lower than the early universe. Here are some of the usual suspects of those. So I think it's pretty robust. Our team and other groups have gone over an exhaustive study of systematics and variations. I don't think that there's any internal inconsistency or evidence of excess noise to speak of. Rather, we see a pretty consistent story for this tension, particularly from JWST, which I think has really made it clear that errors in past Cepheid measurements from Hubble are not a cause of the Hubble tension. So this leaves us with a really great puzzle, a very interesting one, certainly. Is there something missing in the Lambda CDM? Well, it certainly is not a very deep theory, and so we expect there will eventually be things to learn beyond Lambda CDM. Is this indication of new physics in it? I don't know, but it's intriguing to think so, and it has certainly become a very hot topic. And I will end there, and happy to take any questions that you have. Thank you.
Thanks so much, Adam, for this outstanding, impressive lecture and results and new results and conclusions. So we have time for questions, points, comments, reactions from the audience. So please, participants, raise your hands to formulate questions or comments to Adam, please. So we have a question from Sadak Moshe. So reactivate your microphone, please, and formulate your questions.
Yes, thank you very much. Thanks a lot, Professor, for your helpful presentation. I have a question about modified gravity, which you talked about before. My question has in 2 parts. First, do you think that modified gravity, which is searching for alternatives to gravity, dark matter, and solution to question about dark energy, can solve the Hubble tension problem? And second one is that if you agree, can Hubble tension be fixed by introducing new model by modified gravity, or is another thing that you believe? Thank you very much.
Sure. Well, it's a very good question. I think, as I talked about in the beginning of my talk, we generally assume that general relativity is the right theory of gravity, and we take that as a benchmark, and then we do tests. And then, in this case, we see a tension. I will say that gravity has been tested quite well on many scales, the solar system scale, the galaxy scale, very short scales, and probably all the way up to the scale of the expansion of the universe. So if there is modified gravity, it looks a lot like general relativity. But, the one thing that's unique here in really cosmology in general is that when we go to the largest scales of the universe, we get these, we get dark energy, or we get the Hubble tension. So it's intriguing to think that if general relativity broke down, it would be on the largest scales and that you might modify it in that way. But, you could sort of wave your hands and say, maybe that's a possibility, but until somebody actually comes up with a way to do that, that actually is a better fit to all previous measurements, including solar system, including, Milky Way scale, then we're not really talking about anything in particular. So I think we're waiting for a specific proposal that is better than general relativity.
Thank you for the question and for the answer, Adam. We have another question by Uri Siasipur. So Uri, please activate your microphone.
Hello, do you hear me?
Yes.
Yes.
Yes, thank you very much for the update and your interesting talk. My question is that, okay, with the CMB, we are measuring the Hubble constant and other parameters from very early universe. And from the supernovae, they are mostly at very low redshift. Now, if the new physics, let's say, is somewhere in between, probably the best chance we have to find it is a measurement, direct, for instance, measurement of Hubble constant in sort of middle redshift, for instance, redshift around 5 or something like that. Now, as an observer, do you have any idea what is the best way to do such a measurement? Is there any effort has been done on the measurements at, let's say, this intermediate redshifts?
Yeah, good question. So you're basically talking about we sort of have blind spots in this expansion history. It's calibrated early with the cosmic microwave background, and then from about redshift of 1,000 probably to redshift 1 or 2, where we have supernovae and baryon acoustic oscillations, we assume that the expansion history follows the model. If it didn't, we would like to have observations to check that. There are not a lot of things that we can observe at redshift 5 or 10 to use as cosmological probes. Quasars are one of the few objects that you can observe at high redshift. And so it would be great to be able to use quasars to measure the Hubble constant, or H of Z. The Hubble constant is extra hard because you need to know an absolute scale. But I would be satisfied even if we can measure H of Z, relative distances and redshifts with quasars. People are working on that. I think one of the challenges is the standard candles I talked about in this talk. They start out as very good standard candles, and then we make them a little bit better. Quasars start out as very bad standard candles. They're very inhomogeneous. And so people try to standardize them using relations. But even after standardizing them, they are still, I think, relatively poor standard candles. They have dispersion at the level of a magnitude. And so it's hard to get precise measurements, particularly because you worry about systematics. Things like selection effects become very important when you have a large scatter, because once you have a large scatter, you have to consider that most of the objects you're finding are, the brightest examples because, of the Malmquist bias. Or another concern is you go to very high redshift and there's a lot of look back times. So you might get evolution of your sources across redshift. So this makes those kinds of measurements very challenging. But, I think people should pursue them. Things like strong lensing can be done at relatively high redshift. LIGO someday might push on to higher redshifts. So I would certainly look forward to that.
Thank you. Thank you,
Thank you
Adam.
very much.
Thank you. And we have a third question by Ghosh. So please activate your microphone, yes, and formulate your question to Adam.
Hello, am I audible?
Yes.
So first of all, thank you, sir. It's a really honor to hear from you anyway. It's a great talk. So my question is that because I work on mostly theoretical model, scalar field or cosmology. So I was asking that, as because your research focus on mostly the standard model, whether it's supernova or Cepheid, etc. Do you think that, say, in the CMB, the latest one in, say, what BICEP is trying to do, finding the B modes or primordial one. So do you think that, say, if we get the B modes or some something like, or more about the inflationary scalar field or the primordial gravitational wave, do you think that maybe from the CMB data we can shift the 5 sigma towards say the lower value, little bit of the what the microlensing or the Cepheid JWST etc. is doing? So that's what I was wondering, that I mean, so is this possible that maybe some B modes and primordial gravitational wave data can actually shift the Hubble tension to that side? I mean, like the in so-called the standard candle side.
Yeah.
Sure.
I think more CMB measurements are certainly warranted, and in fact, I think for us to become convinced that there's a problem with the standard model and that it needs to be replaced, we would need to see, I think, tensions in additional probes, and so the cosmic microwave background, of course, would be one of those. And so I think I'm looking forward to what they call Generation 4 experiments, the Simons Observatory, S4, Lightbird, and various ground-based experiments right now that are looking for B modes. Anything that is new, really, that where you have a prediction of what it should look like with the standard model is an opportunity to confirm that or to see a kind of attention. In terms of the ones that are most targeted to this problem, it's been laid out in a few different papers on particularly early dark energy, what parts of the CMB spectrum could show departures. The hard thing with the CMB is the most interesting anomalies we've seen are at very low L. So these are very large scale. So I think you can just barely see them in this part of the plot right over here, where you've seen the residuals, these departures. Unfortunately, this is where we're cosmic variance limited. We only get one sky. And so we would love to observe scales this large in addition to this, but this is it. We're never going to get those scales from additional maps of the cosmic microwave background. Most of the new information to collect is going to be at the high L and then in polarization as well. So I'm optimistic that new CMB data will be important in this problem and cosmology in general.
Thank you. Thank you,
You,
Adam. And the question we have next, Marie-Noël, please, Célérier, please activate and microphone and ask, please summarize the point, the question.
Yeah, thank you for your very illuminating presentation. And my question is, do you think that the sigma 8 tension might be related to the H0 tension? And I mean that could the curves be the same? Or...
Right. Well, there's two options. It's either related or it isn't. And I think that a lot of people have looked at this, and it's intriguing in that it has a similar kind of sense to it, that high redshift, not high redshift, but early universe measurements like Planck, the CMB, that calibrate the cosmological model, predict a value of sigma 8 that is higher than what you generally measure in the local universe, either from weak lensing, from Boss clusters, from peculiar velocities. And so it's very intriguing to think that this is another kind of a tension that is indicating a breakdown in the model. It's less statistically significant. It's not 5 sigma. It's probably somewhere around 2.5 to 3 sigma. Another complexity is, I think, more recent CMB lensing measurements, which use low redshift, are coming in more like the CMB. And so this may not be an early versus late tension, but it may be a scale problem, which would still be very interesting, but would point to a different direction than the Hubble tension. So I think, the jury is out on this. People are still working on that problem, but, this is what we do in cosmology. We don't sit around and applaud the parts of the model that work. We look for parts that don't work to see if we can learn something. And so certainly the sigma 8 tension is on everybody's radar, I think, at this point.
Thank you.
Thank you. More questions, comments, reactions? So the answers were very clear. I briefly allow if you allow me to point out some points on the issue on H0 tension, I would like just to mention vacuum energy, and even a vacuum energy rate could be interesting concept, and in real it has been implemented to describe dark energy and perhaps to explain the H0 tension. And early dark energy, perhaps, which is in the right direction to explain, although have problem, have not, in my view, have not still been implemented as a vacuum energy to be connected with the constant rate set, with the constant value you observe on we observe today. So that is the first question, the first point said, because after all, H0 is today, but is a Hubble rate, and in the same idea, it could be a vacuum energy rate, which constant value is observed in the today, say today of all the range. You are able to do not observe more than -1 set in the dark energy equation of a state. I think it's interesting to see that from, and I have contributed to that in the sense that what is the nature, and that's clarified in some sense the nature of dark energy, which need to be bosonic or a scalar field contribution to the vacuum, because the fermionic contribution, the quantum to the quantum vacuum, is negative. So you need as an energy. So the dominant contribution is bosonic and from a scalar. And because I stop here, and because of your observed value of the vacuum energy set of the dark energy of the equation of a state is in the milli-electron volt power 4, 2 milli-electron volt power 4. The particle, the scalar particle contributing dominantly to that energy density must be in the a particle, a scalar particle in the milli-electron volt mass. And such a particle exists from quantum electrodynamics, exists theoretically, have not been directly detected or observed, and is the action. So the action which has been proposed, as you know, for dark matter, is not for dark matter, it cannot be, it's not in the right scale, but it could be in the right scale and the particle needed for the nature of dark energy, one of the particles set. And with that, I think that if not solving the 5 sigma should clarify the nature of dark energy and the equation of a state, which in my mind, H0 is directly connected to equation of a state, dark energy, and from my mind, vacuum energy, and general relativity as a classical theory. Thank you.
Thank you, Norma, and thank you everybody for joining, and I hope you have a nice rest of your day. Thank you.
Thank you, and just I want to make a toast for you and for all participants.
Thank you.
All right.
So
Bravo and thank you, everybody.
Thank you.
For you is the morning said. So it's 11 o'clock.
Yes,
said.
I'll have mine tomorrow. I'll have mine
For
later.
us,
Thank
for
you.
us, it's possible in France
Yes.
to do champagne. In France, it's always right
Always
time
okay.
to have champagne.
Very
Oh,
Thank
good.
you
even,
very
even
much.
in the morning, it's no problem.
Thank you.
Yes, thank
Good
you,
day.
Adam.
Take care. Bye.
Thank you.
Bye bye.
Bye-bye.
Good wishes. Good
right.
wishes.
Thanks.